So till now we have seen various depth-oriented traversals of binary tree. We looked at pre-order, in-order and post-order traversals, and for each of them we looked at the recursive logic as well as the iterative logic. Now let's switch to breadth-oriented traversal. So we are going to do the level-wise traversal of our binary tree. So what does it mean to do the level-wise traversal? So what we expect is that if I draw my binary tree in this particular way, I want to travel all the nodes first at the root level, then all nodes at distance 1 from the root, then all nodes at distance 2 from the root, and so on. Okay, so that's the way I want to go, and within each level I want to move from left to right. Okay, so that is what we expect. Okay, so let's draw again the tree that we have been following all this while. So the tree is 10, it has left child which is 20, right child which is 30, and 20 has 60 and 50, so there is 60, and then there is 50, and then 30 has 40, and then there is 70. So if I talk about the distance of each node from the root, so 10 is at distance 0 because 10 itself is the root. Then 20, 30, they are at distance 1. Then 60, 50 and 40, they are at distance 2. So if I want to reach node 40 from root, it requires 2 edges. Same thing about 50, it requires 2 edges to reach 50 from the root. And then node 70 is at distance 3. Okay. So when I perform the level-wise traversal, breadth-oriented traversal of this binary tree, the output that I expect is first 10, then 20, then 30, then 60, 50, 40, and then 70. Okay, that's what is expected from the breadth-oriented traversal, the level-wise traversal. Okay, so let's think about the method. Okay, so what should really happen is that if I start from the root, I should be able to store both its children, and within them there should be order, right? The left should be stored first, it should come first, and then the right, and then within the children of 20 and 30, the children of 20 should come first, and then the children of 30 should come later, and so on. Okay, so if you think about it, it really fits in the first in first out processing of the data. Okay, so most probably Q would be helpful for us. So let's write the logic for our function, which is level-wise traversal of our tree, and as input we receive a node. Okay, the first thing we should check is if our node is null. If our tree is empty, there is nothing to do. So if our node is equal to null, in that case, well, there is nothing to do, we simply return. Okay, if that's not the case, if our tree is not empty, then what should we do is we should create a queue. So let's say we are going to have a queue, let's name it queue, and then create a new queue. Okay, so create new, and the capacity again will say that it will be at the most number of nodes in our tree. So let's write it as tree dot node count. Some implementations in certain programming languages might not require you to specify the capacity at the beginning. They would grow on their own, but we will not go into those specifics right now. So now you start with your empty queue, and let's add our current node, right? So we'll say that queue dot add the node that we have received, and now we have to go to the queue and process each element. So I will do something while my queue is not empty. Okay, so I'll check if queue is empty and then negate it while my queue is not empty. What should I really do? Well, I should take out an element from the queue, fine, So I'll say that q dot delete, and that should be equal to my current node. So I've got my current element. Once I get the element, I should do the processing for the element. So whatever is my code specific to the traversal, remember in each of the previous traversals we talked about action that you require per node. Okay, so depending on why you are doing the traversal, you might have the required action for the node. Okay, and once you do that, then what you want to do is you want to check if there exists the left child and then add it. So we'll say that if current dot left is not equal to null, then what should we do? We should add it. We should add to the q dot add current dot left. And similarly, if the current dot right is not equal to null, then we should add to the q current dot right. Okay, and once we have done that, we are done. Okay, and that actually completes our level wise traversal of the queue. So let's ask question about the time complexity of this method. So what is going to happen is each node of this tree is going to be queued only once as a child of the parent, and then we are going to delete it from the queue only once. So all these add and delete operations, they account for constant number of times per node or theta n times for the whole tree. And then we assume that this operation that we are doing for the node, the task specific operation that we have to do per node is of constant time complexity. So the total time complexity of the algorithm remains theta n.